All righty. Well, thanks everyone for joining us this afternoon. This is the month that we are dedicating to using mathematics and computational thinking. I am Robin Deems, one of your science consultants with the Department of Education. And along with us, we have Ms. Kathy.
Good afternoon.
Kathy Holmes and Lydia Hunter. Lydia, you want to wave to everybody?
Hello, glad you could join us.
And as one of our very special guests, we have asked one of our math consultants, Ms. Anna Canalongo, to kind of walk us through this because there is so much of this that is based in mathematics. And we thought she would be the perfect expert to kind of take us on this journey.
So welcome everybody
for joining us.
Welcome. Thank you for coming. It's been exciting working with the science book at the department and just learning about how much math and science relates in our different practices, even though I know that they do. It's not very often that I dig into both sides. So it's been a fun experience for me, and I hope them as well, as we plan this activity for you to kind of just see some of the overlapping principles between both of them. So I'm going to start you off with just an activity. So this is a Guatemalan sinkhole. In 2010, an enormous sinkhole pictured below suddenly appeared in the middle of a Guatemalan neighborhood and swallowed a 3-story building above it. So in the chat, I want you to just put down, what do you notice? There in the cloud there's a what do you notice and what do you wonder sign. And I want you to just basically focus on the what do you notice. Okay, now I want you to think about what do you wonder? Start putting your wonderings in the chat. Oops. Okay, so we have a lot of good wonderings, which related to your noticings pretty well. So you wonder how deep it was. We have our compassionist, I wonder if anyone is hurt. What caused the sinkhole? So causing it, how deep is it? I wonder what caused it. How deep is it? Did anyone fall in? Will it spread? That's a big question, especially if we have a house in the corner there. Will it get bigger? I wonder if the buildings around it are now compromised. Was there any loss of property and life? Can we fix it? Where's the building it swallowed? How can we prevent this? That's a good question too. So because it's the mathematical computational thinking, we're going to kind of focus in on some of the math questions, although those may not be the most relevant questions, especially if you have a building on the side of the sinkhole, but it's kind of going to be one of the ones we explore today. But it is relevant to no matter what question you have. If it grows, you want to see how big it is now before it grows, right? So the mathematical part may come into some of these other questions later on as you're trying to quantify things. So we're going to talk about how big is the sinkhole. And the sinkhole has to talk about volume, right? So we're trying to talk about volume and the shape of the sinkhole, right? So if you were going to talk about the volume of a sinkhole, here's another picture of it there. What would be a guess that would be too high? And so in the chat, just if we're talking about the volume of the sinkhole, what would be a guess that would be too high? And then what would be a guess about that would be too low for the volume of the sinkhole? And what's your best guess? And you can use the metric system because you're science people, or if you want to use the standard system, that's okay too, because you estimate better that way. Either way is fine. So in the chat, just put your too high guess, your too low, and your best guess. Okay, and the reason that I'm asking the questions too high, too low, and best guess is that really gets your students think about numeracy. What we hear from everybody in the workforce and in our students that are in our classrooms and even in our higher ed math faculty is that students have a very hard time estimating with numeracy. So anytime we can give them a chance to estimate something, we try to do that. And so they can kind of also, as you know, students have a hard time thinking back to their question if it's reasonable or not. So this is kind of trying to kind of get them into that reasonable range. So if they get something that doesn't make sense, it gives them pause and say, okay, at the end, this doesn't make sense. Okay, so now what do you know and what information do you need to know? So in the chat, just kind of talk about what you know and what information you need to know. So one thing you might know is what shape does it approximate? Like what kind of shape is it? You're thinking about volume. Yes, you do. So it's a cylinder. That means we can, if you think it's a cylinder, then that helps us with our toolkit, right? We know some things about cylinders that we can pull from in our mathematical toolkit. So that's good. What other information do you need to use some of those tools? About 1 street wide. So we want to find the volume of a cylinder. What kind of information we need to know? You need to know the metric system, maybe. Okay, the depth and the radius, right? So I'm going to give you that information. It's in Act 2, we're estimating. And now we're also creating a mathematical model to describe the situation. So if the diameter of the sinkhole is 20 meters or 66 feet, and the depth is 30 meters and about 100 feet, and a piece of paper next to you or wherever you're at, create a mathematical model to describe the situation. Now, a model can be a lot of things. It can be a graph, it can be a picture, it can be an equation. So any of those things, describe the situation with a mathematical model. Might be an inverted pyramid, it might be. So you could draw your sinkhole as a pyramid and use the same information. You would still need to know the diameter or the length across, right? If it's a rectangular pyramid. Or cone, it might be cone because it's more circular, right? I would assume. I think in Zoom you can do the little response button. So if you have your model, once your model's made, kind of put the little thumbs up sign. So Tracy, welcome. We are trying to find the volume of this sinkhole.
Sorry about joining late.
No, it's fine.
Glad that you could join. No problem. Just a little bit of background. This is a real picture from Guatemala, real sinkhole that happened in 2010. So we're just looking at this picture and asking some questions about how do we figure out the size of this?
We have some information on the side there to the diameter and the depth of the sinkhole.
You said we're finding the volume.
Volume. Mm-hmm. And most people think it looks like a cylinder, but one person thought it looked like an inverted cone.
Yeah, I was thinking cone
Feel
also
like.
from the angle that I'm looking at, because it doesn't look like it kind of tapers.
Yeah, so here's the other pictures. But it could be a composite shape, right? So I saw one thumbs up that they're done. We have two that are have some kind of answer. Give you guys like another minute. Okay. About 30 more seconds. Okay. And if you need more time to work, that's fine. We're just gonna move on for the sake of the presentation. So Act 3 is the big reveal. So Act 1 kind of builds, right? Act 2 gives a little more information. Act 1 kind of piques interest. Act 2 gives some more information, has kids start to work. And then Act 3 is like the big reveal. What's the resolution to it? Okay. And so can someone share what they found? Okay, I'll put what we found in the chat. That would help.
Sure, I don't mind sharing if you want someone to share out loud.
Okay.
Thank you, Elizabeth.
Oh, you're welcome. So I made the assumption that it was a cylinder based on what I observed. So with you giving us the information that the diameter was 20 meters and that the depth was 30 meters, I used the formula for the volume of a cylinder, which is pi r squared, radius squared times the height. So when I plugged in the radius of 10 meters and a height of 30 meters, I came up with 9,420 meters as the volume.
Great. Did anyone get anything different?
I used the formula for cone because,
Okay.
and so I got 4,000 cubic meters.
Okay. Anybody approach the problem differently? Okay, students may get different answers depending on what they use as pi. If they use 3.14, if they use a pi button on their calculator, right, that might come up with a different answer, which are, and then you can talk about approximations. Some students might use feet because they're kind of able to estimate in feet more. I know with science, you guys like to kind of promote the metric system. Somebody could say, do some kind of composite shape, right? So there's a lot of different ways you can kind of do this. Some kids could have drawn pictures. Those are all okay ways of approaching it. This was a pretty simple problem as far as mathematical modeling goes, but I kind of just want to show you the 3-act task. So we're going to talk a little bit more about what mathematical modeling is, what science is, and then we're going to kind of let you guys dive deep into some breakout rooms, or maybe one breakout room. Okay, and then you also have next steps. So sometimes you talk about, could you revise your model to make it better? What new questions do you have? Now, in this case, our model is pretty much a formula, so there's not much we could do to make it better. Now, maybe, right, if we want to be a little bit more accurate, we could kind of talk about, well, maybe it's a cylinder for part of it, but it's not a cylinder for all of it, or it's not a complete cylinder. Maybe it's like an oval, you know what I mean? You can talk about like maybe the top's not a complete accurate circle. Maybe it's more an ellipse or an oval or something like that, right? So, but we can talk about, maybe we'll just share because we have out loud, since we have just a couple people on the call. What new questions do you have? After you found the volume of this hole, what new questions would that bring to mind that you could explore?
I started to wonder if there was any water in the bottom of the hole. And if there was, what do I count as the volume? Do I count the unoccupied space or the space created by the shape of the sinkhole? Okay,
that's a good one.
Well, my background's more like earth science, so I was thinking like, well, what is that? What's that material? Like, is it, what kind of rock layer is it? What kind of soil is it? What kind of porosity does it have? Things like that.
And then Jenny had some good quotes in the chat too. How are you filling that much volume? How much volume is the building that was lost? Those are important questions, especially if it's your business that's lost. Anybody else? Okay, so what I did with you guys is a 3-act task. And this is something that's kind of been in the math world for a few years. It's picking up a lot of steam. It's a way to kind of model mathematics, and it seems to be very engaging for students. There's a bunch of free mathematical 3-act tasks out there you can use, but it usually has a hook and then kind of like a brainstorming question and answer like we did. So like there's something exciting like a sinkhole. Why is that sinkhole there? What's that all about? It really draws the kids' interest. It's usually a photo or a video or something like that. And then there's the brainstorming question answering, and that's kind of where the problem is posed. Act 2 is the model. That's where kids make an estimate. Then they say, let's give something high, let's give something low, let's kind of estimate something in between, trying to kind of help that numeracy develop, help kids get the idea of reasonableness. And then it moves on to the mathematical modeling part. Can you draw a picture of that? Do you have a formula for that? Now, some of them, this was a fairly easy one because it was straight up volume of a cylinder or cone, depending on how you looked at it. But there's some that are a lot more complicated with a lot more variation going on. So you have a lot more discussion. And then the third step is the resolution, the sequel. So the resolution is the solution. You kind of reflect on it. Could I have made it better? And then what are your next steps? Can I revise? Can I elaborate? Can I take this into something else? Maybe how much does cement cost to fill that in, or whatever it is you fill it in with? So that's kind of the 3-act task. I kind of want to just kind of pique your interest with that. So now I'm going to hand it back over to my science ladies, and they can kind of talk about the nature of science and all of the good stuff that goes with it. And then we'll move into mathematical modeling.
So we've seen all of this precursor. So how does it tie into what we've been looking at throughout our whole PD series? We've been talking about the nature of science, and incorporating the nature of science in instruction really allows students to engage in the doing of science. It showcases the norms by which scientists study the world around us and communicate about their work, making students' knowledge more meaningful and embedding that knowledge more deeply into their worldview. It also helps children recognize that the work of scientists and engineers is a creative endeavor, one that is deeply affected the world in which we live. Next slide, please. So let's talk about where we've been and where we're going with this particular presentation. We started off by going through the scientific and engineering practices. We looked at asking questions and defining problems that can be investigated and solved in the natural world. Students create investigations to solve problems or learn about phenomena. From the investigation, we collect data that helps to inform that process. The last session in this one focuses on mathematical and computational thinking. Data is used to develop models that aid in the interpretation of results and the drawing of conclusions. Next slide, please. Although there are differences in how mathematics and computational thinking are applied in science and engineering, mathematics often brings these two fields together by enabling engineers to apply the mathematical form of science theories and by enabling scientists to use powerful information technologies designed by engineers. Mathematics builds the bridge. Both kinds of professionals can thereby accomplish investigations and analysis and build complex models, which might otherwise be out of the question. In both science and engineering, mathematics, computation are fundamental tools for representing physical variables and their relationships. This slide represents a range of tasks from K to 12 can be used to develop mathematical modeling. Take a moment to read the underlined phrases in each grade band to see how the process builds. In order to kind of see how these things come together, these highlighted words kind of pull out those major events in each one of the grade bands. Next slide.
Okay, so what is mathematical modeling? So we're going to kind of pivot from there. So you can kind of saw when I first looked at when Kathy and Robin and Lydia asked me to do this presentation, I kind of started reading over all the information they sent me about mathematical and computational thinking. And what stood out to me is really what they were describing is the mathematical modeling process. And so first question is, what is mathematical modeling? Now, it's described differently in different organizations, different resources. So I just pulled a few for you guys to kind of get an idea. So mathematical modeling is a process that uses the mathematics to represent, analyze, make predictions, or otherwise provide insight into real-world phenomenon. That's from the game model. In the standards, modeling means using real-world mathematics or statistics to describe, that is a model, a real-world situation and deduce additional information about the situation by mathematical or statistical computation analysis. And another place in Arizona Progressions, it talks about the purpose is to understand reality. So the purposes of mathematical model is to kind of understanding making something simpler to understanding the underlying reality that's posed in the problem. And it has to do with real-world context, which you as science teachers do all the time, right? Math teachers, we have to kind of push our teachers to do a little bit more of that kind of stuff. But that's kind of what mathematical modeling is about. And that kind of overlaps what your processes are or your practices are. And so we have different types of models that should still be there. So last time I met with some of you, we talked about statistical models. This time we're talking about mathematical models. And so what is a model versus modeling? So a model is a tool that uses mathematics to represent a real world situation. There could be multiple mathematical models for any given scenario. With the one we did with the 3-act task, a formula seemed to be the best model, but in other tasks, you might use a graph or you might use a table or you might draw a picture. There could be different types of model. And it also depends on what the student knows. The more tools the kid has in their tool belt, the more likely they are to use different models, right? So you all had the cylinder and the formulas in your tool belt, so you were able to use those. Some students have more sophisticated tools than others, depending on their grade level and or ability and experience. The mathematical process, though, is the creation of such a tool. So it requires creativity and brainstorming. It could be something like, is it worthwhile to drive across town to get gasoline, right? And kids might draw pictures, they might have to make assumptions, they have to do all these different things to evaluate whether it is or not. One of the mathematical models that come to my mind regularly that I want to assign to some of our students so I can kind of figure out is Giant Eagle gas mileage. In my Giant Eagle, my grocery store nearby, I can get points and I can either use them to take percentage off groceries, or I can take get points off my, or I don't know, increments of 10 off the gasoline. So when is the optimal time to use those extra bonus points, right? So kids could draw pictures, they could do math, they could do all sorts of things to kind of do tables to organize their information. Validating the model is important in the process. Refinements are also important. Your model might start off simpler, but then as you gain new information or your thinking becomes more sophisticated, it may become more detailed. It also depends on who you're communicating with your model. If you're communicating to a general audience, it might be very simple. If you're communicating with experts in your field, it might be a lot more complex. So what are some types of mathematical models? Equations, graphs, diagrams, geometric illustrations, tables, spreadsheets, simulation, and experiments. So from here, we're going to go into breakout rooms, and Robin will put the part in the chat. I don't know, are you guys all 6th grade and above on the call? So Jenny's 6th grade and above, Tracy?
I work in an ESC, so I deal with all grades, but I was a middle school teacher for 25 years, so I took more middle school.
Elizabeth and J Camp. What's J Camp? What is your name? Your first name?
It's Julie, and Elizabeth and I are teacher partners. So we're both science support teachers. So 6th grade would definitely be in our realm.
Okay, what about you, Elizabeth?
See, I taught mostly junior high and high school science.
Okay, so we're gonna go, so there's 2 breakout rooms where we go, and we're gonna start in the 6th to 12th grade one. There is a K5 one there. So like if you at the ESC wanna use the activity and go to K5, you can do that as well. But we'll just work at the 6th grade middle school level. So I'm gonna stop sharing my screen for the moment. Where's stop share? And we're gonna have everyone go to the Google Doc. The 612, there should be a 612 breakout room there. And the slide should be green if you're in the right section.
Has everybody found the Google folder okay?
Was that in the original email, or?
It should be in the chat.
It was in the chat. I'll put it in the chat again for you. Once you get into that folder, you'll see a document that is 6 through 12. It says 6 through 12 breakout, and that's the document we're getting ready to work out of.
Okay, I see a couple people in the chat. Let's see. We're in the document.
Yeah, I think most folks are, yeah.
And now everyone's starting to pop up.
Yep, we're good.
Does everybody get in? Okay, so we're gonna go to slide 3 first of all. And when we talked about it as a group, we decided to talk about some current events. So how long does it take to infect a population? That's our question of interest. If you notice in the right-hand corner, we have a modeling process. It's a very simplified one. We're gonna work with the SPIES analyst model graphic of a modeling process. And today we're gonna be SPIES. So what do SPIES do? You guys can feel free to talk now and not just use the chat.
So I would say SPIES kind of like observe the situation, but try not to have any effect on the situation or what it is that they are observing.
Okay, so they're observing. What else do SPIES do?
Steal information.
Yeah, just get information. So what they found out was that during the 9/11 attacks, there seemed to be a lot of SPIES. There was a lot of information gathered, but there wasn't a lot of analysts. And so even though they had lots of information that those September 11th were coming, They didn't have enough people to analyze all the data. So you need spies and analysts. So right now we're gonna be the spies, we're gonna be the analysts in the next couple slides, but for now we're the slides. We're seeking out information. So what information do we need to answer this question? How long does it take to infect a population?
How big is the population?
How big is the population? And if someone wants to type, we can type or we can just talk, whichever you get.
Maybe what is the nature of what's infecting the population and or how diverse is the population?
Okay.
How spread out is the population?
How spread out is the population? That's interesting.
Is the population isolated, like on an island, or I'm talking about connecting bodies of land or cities or such?
Yep. Anything else we need to know?
Maybe how fast something spreads.
How fast something spreads.
And what might stop that spread?
And what might stop that spread? Or at least reduce, slow it down, right? So you can,
Incubation period.
What?
What's the incubation period?
Yeah, incubation period. That's good too. That's very
I would
good.
want to know some details about what exactly is infecting the population. Is it viral? Is it bacterial? Is like what exactly, what kind of pathogen are we dealing with?
Okay, so those are all good questions and they're all relevant for today because we've all been talking about these on the news, right? So how long does it take to infect a population? So we're gonna do a little simulation, gather some information. Okay, so we're gonna ask a volunteer to be patient 0. Okay, we're not actually gonna act this out today, but think of this, we're gonna, as adults, we're gonna kind of visualize what this would look like in a classroom. In a real classroom, you'd have a kid stand up and be patient 0. So imagine patient 0 standing up and showing that they are infected and transmits a disease by tapping one person. So patient 0 stands up, taps one person, the person who gets tapped stands and taps one other person until the whole class is tapped and standing. So then record the number of people infected after 10 rounds of tapping. So before doing all this, we're going to illustrate this with a model in a second. But before doing this, we just want to make a prediction. Predict how many people are infected after 10 rounds of tapping. Just off the top of your head, what do you think it would be? Well, let's actually go to our low-high estimate. What's a prediction that's too low?
Do you want us to just say it?
Sure.
Or use chat?
So we can just say it. We just only have 4 people here.
Less than 10.
Less than 10, okay. What's prediction that's too high?
1 million.
1 million. So somewhere it's between 10 and 1 million, okay? Now, what are some good predictions out there? Let's have everyone between 10 and 1 million.
Well, how long a time is there between the infections?
How long a time there are infections?
Because that'll make a difference.
Okay. But we're just doing our simulation within our classroom, right? So person taps.
So fast.
Yes, I mean, it doesn't matter if it's fast or slow, right? We talked about this as a science teacher. We're just looking at the ends of 10 rounds of tapping. So a round, maybe I didn't define a round. A round consists of one person tapping another round. So
then in the second round, are both people tapping people?
yes.
Like a permutation, okay.
Yeah. Well, actually, no. And that's the next case. This case is they just infect one.
1 to 1.
1 to 1. The next scenario will be that.
So 300?
Okay, 300. Does that sound reasonable? Does anyone else have another prediction?
So just to clarify on her question, the one person only makes one person sick, and then they
Yes.
never make anybody else sick, and they don't get well before this is over, correct?
Yes, yes. And we will get to more advanced scenarios in a second, but we're starting real simple.
So then each round, there's only one person to tap another person. So
Yes.
it's only 11 or 10 or whatever.
Right. So if there's 30 students in the classroom and you're doing 10 rounds, we're just multiplying 30 by 10, correct?
It started with only one student. And that one student hits one, and then that next one student hits one, right?
Yep.
Yep.
Okay, so I think this is a good time to pause and let's have us draw a picture maybe. It's time to kind of go to the next part. So we don't know if our prediction is correct or not, but we will come back to that question. We're going to go into situation 2 for a second, and then we're going to draw a picture. We're just getting some basic predictions ideas there, and then we're going to go back and we're actually going to draw it out and kind of look at it a little bit more closely. So this time patient 0 stands up. So I stand up, I infect 2 people, I tap 2 people, then those 2 people tap 2 more people, then those people tap 2 more people. Does that make sense? So each person just has 1 round of tapping, I guess. And so if after 10 rounds of tapping, just a big prediction of how it's too low, what's too high as far as people being tapped or standing up at the end.
So 10 is too low.
Okay, 10 is too low, but something that's too high.
I'm thinking I would be at least limited by the number of students that are in my class. So
That's true.
over 26.
Yeah, that's a good, I like that. Okay, somewhere between those. Okay. And then you'd have like, then we would have, what prediction do you think is reasonable?
Like 1 hits 2 and 2 hit 4 and 4 hit 8 and 8 hit 16, that.
Yep.
So like, I don't know, what's that add up to? 1600 something? I don't know.
Okay. All right, so let's move on. Now we're gonna model it. So we did the spies, we kind of get, let's move on to the next slide here. Go to the slide 9. There you go. So a model, hold on, where did we go? I lost my slide here. Patient 2. Okay, now we're gonna be analysts and analyze the data, right? Maybe I skipped ahead too much. Actually, let's go back. Sorry, I lost track of your slides. Can you go back to the slide that's question? Yeah, that one there, slide 8, sorry. Okay, so how long does it take to infect a population? So now you're gonna draw a model. Draw a model of the 1 tap situation and draw a picture of the 2, not necessarily a picture, a 2 tap situation. So you don't have to do a picture. You could do a table, you could do a graph, you could do a picture, and just to kind of show what happens in each round of tapping. The number, think about the number of new people that are infected and the total number of people. And we'll give you guys about 4 or 5 minutes to do that. Well, we'll see. Maybe put your thumb up when you're done. I assume it's gonna take you about 3 to 5 minutes. And then if you're done, just put a thumbs up so we can kind of see either that or in the chat. So I think 2 people are done. Okay. You have about 30 more seconds. Okay, since we don't have I didn't put any technological tools in here because I didn't want to force you into one method over another. If somebody can just kind of show their paper, share your model with the group just kind of by raising your paper up to the camera. If somebody's willing to go for it first and kind of describe their model.
I just made a visual,
Okay.
so I'll show it. It's very small.
That's
Not
all right.
You're going to be able to see it. But
Okay.
if one person is tapping and then that person taps another person, I just made a line of singles.
Sure.
If that's correct or not.
Mhm.
And over here we have one person tapping 2, and each of those people would tap 2 until we get down to these little hashtags. So these are each 6 rounds. The first set is affecting 6 people. And if I counted correctly, the second with the double tapping is affecting 62 people in the same amount of rounds.
Okay. All right, somebody else? Thank you.
Mm-hmm.
I was attempting to make a table. So I had patient 0, and then they tapped 1 person. So now 2 people are infected. Is that right?
Mm-hmm.
And then those 2 people, then they tapped 2 people. Now there are 4 people infected. And those 4 people tapped 4 people. And now we have 8 people infected. So I just kind of made a table.
Yep, that's fine.
I did. And I did the same thing for the other 0, and then they tapped 2. So now there are 3 people infected.
Okay.
3 people each tapped 2 people. So now we have 6 people. That's kind of what I was thinking. I don't know if that's right, because then I thought, well, maybe I'm not supposed to count the first person. Am I only supposed to count newly infected people? So then I got confused. So.
And that's a good conversation to have with your kids. We talked about that. Do we count patient 0 or do we not? So it kind of depends on what your question of interest is, right? So you can kind of define that as a class. Say, once you start having that question, it becomes a good conversation. Does the initial person, are we going to count them or not, right? We count patient 0, which makes the formula a little bit more complicated sometimes, and it might depend on the level of students that you have. If you do high school, you might want to count that first person. If you don't, you may not, especially if you eventually want to get a formula out of them, and you may not, and it may be good to have different representations. Did anyone else do something different? No?
I'll give it a try. I don't know if you're going to be able to see my screen. So
That's all right.
Oh, maybe you can. I started out with a picture, but then realized I could be much more efficient moving over to a table once I observed some patterns in my picture. So I started out with patient 0. I considered them a member of the population, so I counted them in my total. Then I realized they infected 2 people. And then I realized each of those 2 people would have infected a total of 4 people by infecting 2 each. Then those 4 people would have done 8, but then I noticed the patterns in the numbers, 2, 4, 8. And by the time I got to 16, I was like, oh, okay, there's a pattern here. So that's where I switched over to a table and then just
Sure.
pulling the number of people who were infected for each round. And how many rounds were we supposed to go? I might have gone too far.
10, but that's okay.
Okay, so yeah, I did 10 rounds. And if I press the numbers on my calculator correctly, I came up with 2,047 infected. Now, if this was my class, that means I'm in a mighty big lecture hall. But
Yeah, right.
limitations on the number of students available to participate.
I know, I think as I was thinking about that today, as I was doing this for the first time, I should have probably put school instead of class, right? So, know that. So it depends. So these are all good conversations, and there's a lot of different access points, right? So if you're in a high school algebra 2 class, or maybe even algebra 1 class, you might have these kids start doing equations, right? With exponentials, you might see some graphs, but middle school, you'll probably see a lot more tables and pictures, and that's okay. Or you might see a combination of all these things that they all highlight different things and show different things, right? That's good. Can we go to the next? Can we go to the next slide?
Yeah. Well, maybe there we go. Is it showing it?
Yep. So model is a tool like a picture, graph, and equation that's used to communicate a situation. So you guys just made, as part of your analyzing stage, you made a model. Now we're going to use the model to make sure that it works. So we I had you share your model already and communicate it. So we already kind of did that. You kind of already talked about explain how taps are related. Actually, we didn't do this. Oh, let me go back. Go to the next slide, please. So we had you share your models with your classmates. We kind of did that already. We could talk about how long it takes to transmit a disease. Now, in this case, we're not doing long as far as seconds or days or minutes or hours. We're doing long as a number of taps, right? So you can define long however you want. We defined it as number of taps because it can illustrate things pretty well. At the end of this presentation, you'll see a resource, or I think Robin put in a different resource section. There's actually a video, I think of a college physics course, where they kind of show all the taps and everyone standing up in a lecture hall. That's kind of pretty powerful. So the question is, how are taps related to transmitting a disease? Now, this is where the real world comes in. We did a model that kind of shows the situation, simulate a little bit, but now we want to bring it back to the real world because tapping isn't really important, right? But the transmitting a disease is. So how do taps relate to the real world?
Well, the tap equated to the infection, right?
Mm-hmm.
So it could be breathing next to the person, coughing on, touching a doorknob that they touched, however you transmit that.
Exposure.
Mm-hmm. Maybe exposure, maybe not, because maybe you're exposed, but you don't get it.
Sure, maybe that's true. Yeah. And then you could talk about how your model shows.
So transmission.
Right.
Okay.
And so we can go further into this modeling and talk about what it means, explaining how the model shows the importance of staying away from other people when you're sick, right? Don't come to the office or the classroom when you're sick. You're going to transmit that disease, right? You can't tap anyone if you don't see anybody, right? So that talks about like kind of social isolation. You can talk about the different classmates models, what they highlighted, right? What the tables highlight versus what an equation highlights. You can talk about how to make improvements to the model. You can talk about different situations. What about a 3-tap situation? Then what happens to your model? Like, let's say somebody goes out and infects 3 people because they talked to 3 different people. How would that change? Talk about new questions that they can explore. Next slide, please. Okay, and these are different ways you can extend the question, right? And I know that some of you guys brought some of these things up already. What happens if you talk about the whole Earth? What about if you talk about where there's only 30 students, but the you keep the class size constant, but the time it takes to infect the whole class size varies. So that's a little bit more complicated than the TAPS. The TAPS is the simpler version to kind of draw a picture of. What happens if the virus spreads to 3 new people every week and 2/3 of the population is immune? So you can start playing with immunity numbers and have kids draw pictures of these things. What about if the virus kills the host? What about the host kills the virus? So you can talk about all these different scenarios and have kids come up with scenarios and show the different models and kind of talk about, well, okay, that's maybe why we wear masks, because maybe it's not 100%, but maybe it reduces the spread, right? And you can kind of show all these different things. And the next slide, please. And this is just if we wanted to, instead of having them stand up and tap, if you want to do it virtually, because I know a lot of things are being done virtually right now, you can, there's like a bunch of circles there. You can actually have them kind of cross them off as people get tapped on a screen or a whiteboard or whatever you guys use virtually to use. You can just copy and paste. This is an image here. You can just copy and paste that image into something else. There is a lesson that's on the resources that kind of some of this stuff is pulled from, but modified a little bit if you want that as well. So we're going to pause there, and then we're going to go back to our presentation and just kind of close out really quickly.
Is there a simulation that does something like this that you found?
Yeah, there's some graphs and stuff where you can control things. We just found out that Flash is no longer working, so I don't know if it's still there or not. But there was where you could manipulate a bunch of things in the resource kit if you want to look at that. I don't know if it's a resource kit, but our list of resources. There's a bunch of different ways to do it. This one we want to do because then the K5 can do something similar. You can have all the kids stand up and share. It was really easy to see. If you look at the YouTube video on the physics, it's kind of interesting too, as you see how fast it goes when you tap 2 people versus 1 person. It's a pretty good illustration also. It's a little bit more complicated mathematically to kind of show it that way when you're running into it. So I kind of reframed it a little bit.
But I would definitely go look at that video now, because that really will give you a visual of what we just ran through.
Okay, now I'm going to try to share I don't see my Zoom controls anymore. So I can share my screen. The Zoom controls kind of got hidden somewhere.
Move your cursor to the bottom of your screen, Annie. They pop up?
No.
Do you want somebody else to put
Here it
it
is.
up?
Wait, I got it. Here's exit. There it is. Okay, I found it. Okay, so we're just going to go through this. I know we only have about 10 minutes left, so we're going to go through this pretty quickly. A traditional math class versus the modeling focused class talks more about concepts. You apply then practice. It's inquiry-based, student-centered, team-centered communication. It sounds a lot more like a science class, right? Mathematical modeling than it would be a traditional math class where you write examples on the board and practice. So in the math world, we're really pushing some of these modeling problems. And so you can think about how to interact with your math teacher and help them in some ways model, because they might not know some of the context that you know use math. And you can kind of bring those together. So we encourage you to work with your math teacher as well and support each other. There's a variety of different graphics around mathematical modeling, but similar processes. Here's the one in the standards. You present a problem, you formulate a question, you do some computation, interpretation, validation, and then reporting. That's the one in the math standards. This is the one we just did. It's very easy. Even little kids can do it. High school kids can like latch onto this. There's not as many steps to remember. You spy, you gather information, you analyze the information, and then you communicate your model and verify that it works. This is in the game model. This is the report that's all about modeling here. You can look at this more in depth later on, but here again, there's a lot of circles and arrows, which is a little bit more confusing to kids. Here's the Bloom and Ferry model, understanding a task, establishing a model, using mathematics, explain the results, and maybe go back and revise. But there's always this revision process. That's the kind of the key, that it doesn't end. You go back and you refine the model or you revise the model. A computational thinking problem is similar. You define the questions, you abstract to computable form, you compute, and then you interpret results. And so what's your role as a teacher? Your role as a teacher is to provide appropriate engaging tasks, understanding of content to ask, assessing, and advancing questions. You want to have a task that encourages the mathematical modeling, and especially at the content level that you want to kind of pull out the kids have in their toolbox. You want to understand the content well enough to ask questions to assess where students are at, but also to advance them, to push the envelope a little bit, to make them think a little bit harder and longer. If you want them to get this math concept or this science concept, how can you take where they're at and push them a little bit more? Peer collaboration, a safe environment that encourages a growth mindset. Also understanding of content to support individual student perspectives. You might have a kid draw a picture, you might have a kid use a table. So you need to be mathematically fluent to understand enough of what they're trying to do, especially as there's so many more math strategies now in the classroom. They may come up with something, they may divide in a way that you're not used to, or multiply in a way that you're not used to. So being familiar with some of those math strategies is helpful. As a teacher, you can kind of take what they have and then build upon it and start with their understanding and build. And so what does this look like? And I know Robin has pulled these out and put these in a handout so you can see them a little bit better. But here's some teacher look fors and some student look fors to see if mathematical modeling is happening in the classroom. And since NC team actually paired this with using appropriate tools strategically, which makes sense. Like tools are equations, our formulas, our graphs, those can all be tools, as well as computers. Like we can analyze a vast amount of information using computers like spreadsheets, things like that. Some of the simulations online could be a tool. And then here's another student rubric. If you want a rubric about what it looks like to see if kids are modeling with mathematics, it goes from needs improvement to exemplary. And here's some tips. Just modeling like real life is open-ended and messy. You might not get a final answer, and that's okay. The process is more important. When students are modeling, they have to be making genuine choices. Start big, start small, just start. And if you're going to assess something like this, it should focus on the process, not necessarily the end product. Although you do want them to have a product that, you know, is not not done well. You want it to have, the end product may not be the end result, but you still don't want to encourage like sloppy habits, if that makes sense. And modeling does not happen in isolation. That's why it's good to have other content to kind of meet each other. And there's a bunch of mathematical modeling it's not telling kids to copy how you're doing. It's not just necessarily using manipulatives. That's probably not as pertinent to a science teacher, but it would be to the math world. Just because you're using a graph, equation, or function, even though those are models, it may not be modeling. True modeling is that whole process we kind of went through. You start with a real world situation, and it's not just having a real world situation then doing the math problem. It's a modeling problem is all about the context. It's not just taking a situation, then isolating it, do the math, and then come back to it. It's not beginning with mathematicals and then moving the real. It's basically not separating the real world from the math problem, is what those two last bolts are about. It's not beginning with, I think I did it twice. I may have that twice.
Yeah.
Okay. And then potential instruction strategies for using computational mathematical thinking. I got this from one of your Science-y websites, and it says just provide opportunities for students to perform calculations on their gathered data, such as finding that mean or average of several trials. Pulling in that statistics is always helpful too. There's a lot in statistics you guys can pull from at the statistics standards. Computer programs to analyze large sets of data, create activities with scientific questions and have them that require mathematical or computational thinking. Using tools, measurement tools such as cylinders, thermometers, balances. Have older students decide whether to represent their data in different ways, such as ratios, percents. Really push those older students to use the tools that they have. They have much more sophisticated tools in their math class that they're not using in their science class. So push them to kind of use those things that they have. Talk with the math teacher to figure out what tools your students actually have in their tool belt. Engage students in investigations that require them to use mathematical operations. So like subtract quantities to determine the volume of an object. And there's some references from places I've taken it from. So I think that Robin may have taken these out of here too. And I'll let Robin finish it off, but thank you very much for coming to learning more about how to integrate math into science.
Awesome. Thank you so much, Annie. So thank you guys all for joining us. If you would like to kind of delve a little deeper into working with some of the computational data, join SECO for their webinar that's going to be on the 21st of January. And the feature program will be NASA. I know they're going to be doing some work with the My NASA Data project and using the data that they have available to show you some things that you could actually incorporate in your classrooms. And then we'll be back here next month on the 2nd of February, where we will look at constructing explanations and designing solutions. So thank you so much. Like Annie had mentioned, there is a resource list in that Google folder that I shared with you. And the video for this will be posted on our resource page in probably 3 to 4 days. So feel free to stop back in, and we'll have the link in there so you can share it with your colleagues. So thanks so much for joining us, and we'll see you guys next time. Bye-bye.
Thanks.
Thank you.
Thank you.